So we know that dark colors absorb energy really well, light colors reflect energy really well, which is why summer clothes are usually lighter. And this is pretty important. The best absorbers make the best emitters. So the better absorber you are, the more energy you're gonna absorb, and that's why you're gonna be really good at giving it off too. All right. So just to understand why this is all happening, we know about Roy G. Biv. Black is actually the lack of color. It's all the colors combined. It absorbs every single color of the rainbow, whereas white reflects every color of the rainbow. So when you see white, you're actually seeing all the colors combined. White light is all of the colors of light combined. When you see a particular color, it means that that color is the only color that's not being absorbed, the only wavelength that's not being absorbed by that thing. So if your shirt is blue, right, this shirt is absorbing every single wavelength except for the blue wavelength. It's reflecting it, and that's what's entering our eyes, and that's what we're processing as blue. All right. So if we think about how we construct houses, around here, a lot of roofs are what color? They're darker roofs, but in Florida, most of the roofs are light colored, right? Why? What do they want their roof to do? Reflect a lot of the light because they don't want their house to get as hot. All right. Now the darker roofs are around here are great in wintertime, but in summertime, not so much. But you have to hedge your bets, right? You have to think, well, I don't know what color to make it. And if we look at snow, does anyone ski? Right. So when you wear your goggles, they're not clear usually. They have a what to them? They have a tint to them because if you don't have a tint to them, you go snowblind, yeah? And you go into the lodge and you're like, whoa, can't see anything, right? So snow and ice are really, really, really good reflectors, which is important because if we look at the global map, you see all that sea ice up at the North Pole, yeah? And we know that even though we can't see it on this map, we know Antarctica is all white too, right? Right? So what is that ice? What are those glaciers and ice really good at doing to a lot of the insulation that's coming into the earth? They're good at reflecting it. So that means that the earth is not absorbing as much radiation, which is important because of the greenhouse effect. Okay, so now let's look at this animation and we're gonna kind of see, well, what happens, what's gonna happen if the sea ice at the North Pole melts? What's going to happen? Now remember, this is sea ice, this is not glacier ice. So if this ice melts, it's not going to cause a increase in sea level, all right? Because think about it. If you have a glass filled to the rim with water and ice, and the ice melts, does the water overflow? No, because the ice is displacing as much water as when it melts, it takes up, right? So this is not going to increase sea level, but it will affect the amount of energy that gets absorbed by Earth. So here is the sea ice. And this is the annual change, summer, winter, summer, winter, summer, winter, right? So the sea ice extends in the winter, shrinks in our summer, which makes sense, but if we look at the square kilometers, the area of sea ice, what's happening? What's the trend that we're seeing? The trend of sea ice, it's decreasing. So it does fluctuate. Now I want you to think about it. Here's the sea ice. What is this white ice doing really well to insulation? It's doing it what really well? It's reflecting it. If that white ice turns into blue water, a lot more insulation is going to be absorbed. And then how is that going to affect the ocean temperature? It's going to increase it. And how is that going to affect our climate? Average atmospheric temperature. It's going to increase it. Now here's an important component of climate change. Listen, if the amount of sea ice decreases, the amount of insulation absorbed will increase. Okay, if the amount of insulation absorbs increases, the average temperature of the oceans will increase. Is that okay? All right, one more. If the average temperature of the oceans increases, the amount of sea ice will decrease. Okay. If the amount of sea ice continues to decrease, the amount of insulation absorbed will increase. This is called a what? It's a cycle, but it's a really important type of cycle. It's called a feedback loop. Okay? Where the end result of the cycle actually feeds the first part of the cycle. Is that okay? So eventually what happens is it's a self-sustaining cycle. It feeds itself. It doesn't need any outside influence. It's like, right? It feeds itself. It's a feedback loop. Last year in life science, did you study permafrost? The taiga? Okay. When, what's happening to the permafrost up in the north and south latitudes? As the temperature increases, as the average Earth temperature increases, the amount of permafrost that's thawing increases. Yes, is that okay? So the permafrost is not okay. As the amount of permafrost that melts increases, the amount of methane that it's releasing increases, because now all that methane that was trapped in the frozen tundra and the frozen permafrost, as it's coming out. Okay. As the amount of methane in the atmosphere increases, the average temperature increases. Oh boy. As the average temperature of the atmosphere increases, the amount of the permafrost that's defrosting is increasing, releasing more methane, which increases the temperature, which makes more permafrost melt. And that's another, what do we call that? It's a feedback loop. It's a self-sustaining cycle. And what's happening with our climate is we're reaching the point where we can't shut it off. It's going to keep on, it's going to keep on feeding itself. So it's a concern. All right. So the sea ice, getting back to the sea ice, it's really important that you understand that, like, the ocean's very dark, and the ocean is a really good absorber. Ice is really light, and it's a really good reflector. So that's important when it comes to the amount of insulation that the Earth is taking in or reflecting. All right? Okay. And so here's a model of smooth and rough surfaces. If you want to get a good reflection in the mirror, what does the mirror have to be to get a good reflection? Very smooth, yeah? If a mirror is all rough, like a piece of glass is all rough on the mirror, are you going to get a good reflection? No. So smooth surfaces reflect really well. Rough surfaces, when the light comes in, sometimes it gets banged around in here and it absorbs some of that insulation. So smooth surfaces like ice reflect really well. Rough surfaces like forests absorb really well. Okay? All right, so that's the actual end of Notes Pack 1. The rules of absorbers and reflectors. Any questions on that? Okay. So then last night you should have watched an ed puzzle that went over all the different types of meteorological instruments. Now we're in the beginning of Notes Pack 2. All right. So we have to measure wind. We have a wind vane or a wind sock. You see these at the airport? You ever see these at the airport? It tells the pilots what direction the wind's coming from and the air traffic controllers. Or a lot of times you'll have a wind vane where the tail or the rooster or the whatever it is, like it goes downwind. We're gonna get to this. What's important about winds are like people. What state y'all from? New York. So you're from New York. What do we call people from New York? New Yorkers, yeah? So your names, or you're kind of categorized of where you come from. So are winds. Winds are named for where they come from, not where they're blowing towards. Yeah, we're going to get more into that, okay? We're going to talk about relative humidity. We use a sling cyclometer. Pressure barometer, because it's measured in bars. Wind speed is the cuppy thing. Anemometer. Okay, it's an anemometer. It's a weird word. All right, there's another type of wind vane. I have one of these in my yard. It's a duck. It's a rain gauge. It's just a graduated cylinder, pretty much. It just measures how many inches or centimeters of rain that fell, and of course temperature is measured using a thermometer. All right. Now, air pressure. All right. Right now, we all have an entire atmosphere full of air sitting on top of us. Right? One atmosphere right now is on top of us. Now, I know that gases are very low density, but do gases still have mass? Yeah, of course they do. And when mass is pulled down by the force of gravity, they also have weight, right? So right now, all of the weight of the air molecules that are above you are being pulled down by gravity. And what are they doing? They're doing what? They're pushing down on you. That weight or that pushing is air pressure. That's all it is air pressure. It's how much does the air weigh on you right now, okay? And we measure air pressure using a barometer, and there's two components, which you should have seen last night. You can use the US customary, which is inches of mercury, and that's one scale in your ESRT. And then there's millibars, which is the metric unit, and that's also on a scale in your ESRT. Do you have any questions on the scale in your ESRT? Okay, so let's take a look at it. All right. The left side is in millibars, right? And the right side is in inches of mercury. Hg is the symbol for mercury, okay? Now, I would like you to look at, you should know this from last night, but I would like you to look at the tick marks that are on the millibar side. And what is each tick mark worth? Not the labeled tick marks, but the individual tick marks. How much is each tick mark worth on that scale, on the millibar side? Everyone agree with Frankie that it's 1 millibar? Yeah, yep. So you're gonna write that here, 1.0 millibar. You're gonna write that on the left side where it says millibars increment. And let's prove it. This is 980 right here, going up to 984, 981, 982, 983, yeah, 984. So each tick mark is worth 1. Now, be careful. What is each tick mark worth on the inches side? Pick 2 consecutive amounts and then figure out what each tick mark is worth to get from one to the next. Will, what do you think? Say again? 0.01. Does everyone agree? He's right. It is 0.01. And the unit is inches. So on the left, we have 1.0 millibars. And on the right, we have 0.01 inches. Wow. Those are really, really, really different scales, aren't they? So be careful when you're reading this, and that if you're reading the left, make sure you know that it's 1 millibar, and if you're reading the right, make sure your increments are correct on the right. Now, there's a mark on here that says 1 atmosphere. If you remember when we were looking at page 10 in the ESRTs, the pressure as you go towards Earth's core, do you remember that? It was measured in millions of atmospheres. Remember that? Millions of atmospheres. Because you know that, like we were just saying, like gases are very low density, right? But solids, high density. So when you're going down in Earth's center towards Earth's core, boy, the pressures are crazy high. And you need a relatively large unit to measure that pressure, yeah? Even liquids. Oh my God, somebody threw my goggles in the pool, in the deep end. I gotta dive down to get my goggles. Have you ever done that? Dive in the deep end? How does that feel on your ears? It hurts a little, doesn't it? Especially if you're playing that game all day, like diving for stuff all day, and at the end of the day, you're like, oh my gosh, my ears really hurt. You know what I mean? Okay? So, solids and liquids, when we're measuring pressure, because they're so dense, we need bigger units. We need larger units. It's kind of like if you're measuring the weight of a car. You use tons, not ounces. Yeah? Not grams, okay? But when we're measuring the subtle changes in air pressure, right? Just tiny changes in air pressure, which you don't even feel, really. You don't even notice them unless you have arthritis, you know? Okay? You have to use much smaller increments to measure those teeny tiny differences in pressure. And that happens in the atmosphere. Now, up here, right above like 1 atmosphere area, I'm gonna make a big H. What does H stand for in terms of atmospheric pressure? When you see them on a weather map, what do they stand for? High pressure, yeah? Okay, and down here, right, down here we have a big L. What does L stand for? In low pressure, you got it. Now, the range of normal pressures on Earth in millibars, it only goes from 9 to 67, 66. The bottom most is 965 millibars, right? That's the lowest pressure. And in order to get that pressure, like you would have to have like the center of the eye of a hurricane or the center of the eye of a tornado. Like that's the only time that the pressure would get that low, like crazy low pressure, right? Or up here, the highest high pressure that we have is 1041 millibars, yeah? So you notice that it's less than 100 millibars, a difference of pressure from low to the low to the high, right? And if you think about pressure, if you see that there's high pressure over you right now, I'll give you a clue. There was really good high pressure over us this past weekend. What does high pressure indicate about the weather? Is it crappy weather or good weather? It's good weather, right? High pressure, think high, yeah, good, yeah. What about low? If you see a low pressure system coming towards you, what kind of weather is coming towards you? Bad weather. So high pressure generally means good weather, and low pressure generally means foul weather. Okay, and this is why one of the most important measurements that you can make is, hey, what's happening to the pressure right now? Is the pressure on a decline, right? Which means that the weather's gonna get, kind of worse. Or is the pressure on an upswing, which means that the weather should get better. That change in barometric pressure, that measurement of pressure, is super duper important when it comes to forecasting. Okay, any questions on that? Yeah. Well, it only can increase so far. There's a max. Like, it can only increase so far, right? There is a limit. And this scale is made based on the limits, the extremes within our atmosphere. Like, if you have a pressure of like 1028, that's pretty high. Like, I don't know if you're really ever gonna get to 1041. I don't know where that would happen, but that would be pretty rough. That would be pretty unusual. Do you know what I mean? So the high and the low, the high on the scale, and the low on the scale, those are the most extreme pressures that you could see. They're not normal highs and lows, but those are extreme highs and lows. Is that okay? All right. Now, what factors affect our air pressure? Like, what goes into just air that's sitting on top of us, not moving? What factors affect air pressure? Okay? Well, the first factor that affects air pressure, okay, well, actually, before we get to that, sorry. How do we show air pressure on a weather map? If they're measured in millibars, lines that connect points of equal pressure are called isobars. Oh, we're going to practice drawing iso lines. Whoop, whoop. Okay? Isobars are lines on weather maps that connect areas of equal pressure. And if you look at weather maps and you see that big H with all those loops around it, and that big L with all those loops around it, those are isobars. Those are lines of equal air pressure, okay? And the same rules that we learned in mapping, we're gonna review these rules from mapping, okay? The same rules apply for isobars and isotherms as contour lines. If the isobars are spaced close together, what does that mean about the pressure? It's very what? Steep pressure gradient, okay? And if the isobars are very far apart, that means a low pressure or gentle pressure gradient. Now, if the gradient is steep, it doesn't mean that you're gonna have a tough hike, like in contour lines. If the gradient is steep, it means the winds are, yeah, okay? We're gonna get more into that, okay? Now, we already talked about this. Air pressure decreases as altitude, what does what? Go back to ESRT page 15, was it? Or 14? Hold on. Oh boy. Oh, there it is. Okay. As altitude increases, what happens to air pressure? As you go up in the atmosphere, the air pressure decreases. Is that okay? At the Earth's, at sea level, what is the average air pressure? 1 atmosphere, okay? Let's see, at 10 kilometers above Earth's surface, what is the approximate air pressure at 10 kilometers above Earth's surface? You have to figure out what each one of those little tick marks means on the pressure. If this is 1, is it 2? 2, 4, 6, 8. No, it's not 2. What is it? 2.5, right? So 2.5, what do you think? Or is it a little less than that? I'm sorry, 0.25, 0.25, 0.25, 0.25, 0.25. It's a little less than that. So at 10 miles up, the air pressure is approximately 0.2 atmospheres. Is that okay? That's why when you're in the plane, again, you have to be in a pressurized cabin. Because when you're flying, you're at 35,000 feet, which is 7 miles. So you're here. You're flying on the top part, in the top part of the troposphere. So you're flying where the pressure is really low. Okay, and then you have to be in a pressurized cabin so you don't pass out because the air is really thin and there's not enough oxygen for you to survive. Okay, so let's make a little graph of that let's make a little graph of that on that page. Okay. Okay, so here we have our little graph here, and on the x-axis this is altitude, and on the y-axis this is air pressure. So if the altitude is low, or if we're at a high altitude, air pressure is low, and air pressure is high. Okay, so if you're at a low altitude, that means you're close to Earth's surface. Tell me about the air pressure. It's high. Okay. If you climb to the top of Mount Everest, or if you go up in a plane, tell me about the air pressure way up there. It's low, okay? So that is the graphical relationship. And that's why it says here, it's an inverse or indirect relationship. Is that okay? All right. So now, what's the next factor that affects air pressure? Temperature. Now we're going back to density. Okay, I need you to put on your density caps right now because we're going to be applying a lot of density in meteorology. Okay, I want you to think about the air that's above you right now. The air above you right now is relatively warm. So even if the air is not moving up or down, side to side, the air above you is warm. Think about the space between the air molecules right now. Are they close together or are they far apart? They have a lot of thermal energy, right? I want you to think about the molecules. If molecules have a lot of thermal energy, aren't they moving fast? Okay, if they're moving fast, aren't they bumping off each other hard? Okay, and then what's that doing to the space between them? It's increasing the space between them. Do you remember when I heated up the brass sphere and I couldn't get it through the ring? Why? Because it was warmer and the particles, the atoms got further apart. Is that okay? Okay. So if the air above you is warm, the air molecules are further apart. You with me? Therefore, the warm air's density is less. Does it weigh as much if it's less dense? Does the air weigh as much if it's less dense? No. Tell me about the air pressure. It's low. Because the stuff that's on top of you is less dense. Is that okay? All right? So, warm air's molecules are further apart than cold air's molecules. True statement, yes? It's less dense and not as many molecules are on top of you, an area to add pressure. Therefore, as temperature increases, let's add a word here, as air temperature increases, air pressure, what? Decreases. And what kind of relationship is that? Let's make a graph. Okay. Oh, I'm in period 4s. Yeah, I am. Okay. We're going to make a graph. Okay. So on the x-axis, the variable that we're changing on purpose is temperature. Cool, warm, and air pressure on the y. That's the dependent variable. That's what's being affected, low or high. Okay. If the air is cool, the molecules are really close together. The air is dense. That's going to add weight. So if the air is cool, tell me about the air pressure. It's high. Good. If the air is warm, it's less dense because the molecules are further apart. It doesn't weigh as much. So tell me about the air pressure. It's low. So what kind of relationship is this? Inverse. Okay, so as air pressure decreases, okay? Is that all right? Okay, those make sense. Okay. This is what doesn't make sense. Okay. Think about those hazy, hot, and humid days in the summer. How does the air feel? Hot, sticky. Does it feel light or heavy? Yeah, it feels heavy. The question is it? I don't know. Let's find out. Okay. We're going to look at two different parcels of air. A parcel means an area of air. Just a piece of air hanging out on top of you. Okay? All right. We will use circles to represent each type of molecule or atom that is found in air. N2, O2, H2O, CO2, and argon. We will put a total of 17 molecules or atoms in each parcel of air. Remember that when a molecule of a substance enters the parcel, a different substance's atom or molecule is pushed out of the parcel. Remember that each box of air must have an equal amount of total atoms or molecules, 17 each. So in the dry air over land, here's Snoopy's cousin hanging out in the desert, there's a cactus. This is very dry air. But even the driest of air has a little bit of moisture in it, okay? So in this box, in this parcel, we're going to make 17 circles. So just spread them out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, we got 17 molecules of air. Most of these molecules are what gas? Nitrogen. So let's make 10 of them N2. One more, okay. N2. So we have N2, 10. We have 10 molecules of N2. What's next, the next most prevalent gas in our atmosphere? Oxygen. Let's make 4 of them oxygen. O2, 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 O2. Is that okay? So we have 4, O2 equals 4. You should have 3 blanks left. Is that okay? Okay, we're going to make one of them argon. We're going to make one of them H2O. And we're going to make one of them CO2. Is that okay? We're going to actually calculate the mass of this air using this. These are the atomic masses, the number of protons and neutrons in each one of these atoms, okay? So we have 10 molecules of N2. What does 1 atom of nitrogen weigh? 14. But these are N2s, which means we have to do 10 times 28 AMU, which equals what? 280 AMU. Is that okay? Do you want me to explain that again? Okay. 1 atom of nitrogen, this is an atom of nitrogen, has an atomic mass of 14. How many atoms are in N2? 2 atoms. 2 times 14 is 28. Okay? And then 10 of those, 10 of those nitrogens, 10 times 28 is 280. Okay. Let's look at oxygen now. What does 1 atom of oxygen weigh? 16. But these aren't O's, these are O2s. So 4 times what? What's 2 times 16? 32. What's 4 times 32? Will? Is it 128? 128 AMU. All right, 1 argon. What is the mass of an argon? 40. And this is 1 argon, so it is 40. So that's, we're going to add 40 AMU to that, okay? H2O. What is the mass of 1 hydrogen? 1. But how many hydrogens do we have? 2. So that's 2 plus, what's the mass of 1 oxygen? 16. So what's 2 plus 16? 18 AMU. So that water has a mass of 18 AMU. Okay, and finally CO2. What is the mass of a carbon? 12. What's the mass of 2 oxygens? 2 times 16 is 32. 32 plus 12 is 44. So that 1 CO2 has a mass of 44 AMU. Tally it up. Add up all of these, and we're going to get the mass of this air. You got it, Will? What'd you get? 590? Is that what? I can't hear you. 590. 510? I'm having really a hard time because I got the noise out there. I got the fan. 510. Does everyone agree? Did you add them up? I need a confirmation of that. Leah, you confirm that? Awesome. Okay. Is it time to go? Oh, darn it. Okay. So tomorrow, what we're going to do is we're going to find out what happens when this dry air moves over the Gulf of Mexico. What's going to happen, you think? What's going to happen? A lot of what is going to come off the Gulf of Mexico? Evap, yes. We're going to find out what happens to that dry air once it goes over a moisture source. I'll see everybody tomorrow.